derivatives. It's kind of fun. I think integration with multivariable functions is even more fun. Um, and our focus today in this lesson is going to be how we visualize these functions. So we'll give some basic definitions, and then we'll talk about some different ways of visualizing these things. So our notation. We are going to say that z equals some function of x and y if we have a two-variable function, or we say w equals f of x, y, z if we have three variables, and so on if we have more than three variables. And some examples of multivariable functions that we're familiar with. And we don't necessarily think of them as multivariable functions because they're so we're so used to working with them. Work is force times distance. So the work is a function of force and of distance. So if each the force and the distance varies, then work is a function of two variables. Area is length times width. So that's an example of a two-variable function. Volume is length times width times height. So that would be a three-variable function. Volume of a solid is a function of three variables. So these are some examples that we've worked with. We haven't necessarily done the type of analysis that we're going to do with these, but these are ones that we're familiar with. We can combine functions of several variables just like we do single variable functions. So just quickly, f plus or minus g of x, y. We're just adding the two functions. This is just f of x, y plus or minus g of x, y. Just like a single variable function. If we multiply f times g, we're just multiplying our functions. That's just f of xy times g of xy. Just like we'd expect. Dividing, same thing. And with this, we don't want g to be 0. And we can do compositions. G of h is just g of h of xy. So just like we've done with single variable functions, we're just adding a variable here. But like I said before, what we're interested in is how we're going to visualize these functions and how we can graph multivariable functions. And I have several of examples from the book that we're going to take a look at. So I just want to go through some examples and talk a little bit about visualization. When we talked about surfaces, when we talked about paraboloids and hyperbolic paraboloids and ellipsoids and all those things, that's one way one tool that we have to visualize multivariable functions. But we're going to talk about some more complicated examples today. So if we want to, and this is page 892 number 38. We want to sketch f of xy equals x times y for x greater than or equal to 0, y greater than or equal to 0, and 0 elsewhere. So we want to figure out what this surface, what this function is going to look like if we graph it. Anybody have any ideas? What do you think? So let's look at our domain here. What if we look at this? What this tells us? What is our domain? Where are we looking? Positive numbers. So it's above zeros. So if x and y are both greater than 0, our function is always going to be greater than 0. So Scott says he thinks it might look kind of like a diamond. So we're looking in the first octant. So we're in the first quadrant of the xy plane, and we're in just the positive z. So our domain.
Is this three-dimensional?
Uh-huh. So our domain is the xy plane, and the range is z is greater than or equal to 0. So because we're talking about x and y greater than 0, our z values, our function values, are always going to be greater than or equal to 0. So let me draw a set of axes, and I'm going to draw them like this time because it'll be a little easier to see this function. So we're looking at x and y values over here. So what I'm going to do is let's pick a z value. Pick a z value that will be easy to work with. 0. So if z is 0, what are x and y? 0. So we know that our function is going to be kind of connected to the x and y axis. So if x is 0, our function is 0 down here. If y is 0, our function is 0 down here. So we know that our function is going to go down to each axis. Let's pick a nice number for x and y, like 5. So if x and y are both 5, what is z? 25? So if x and y are both 5, and I'm going to draw some dotted lines like so. There's a spot in the xy plane where x and y are both 5. So z is going to be up here at 25. Let me put that in red. So z equals 25 here, and this is right above that spot. And if we look at the projection, this is going to make into the yz plane or the xz plane. So z is 25, x is 25 over y, or y is 25 over x. What kind of graphs are those? if we graph this in the xz plane or the xy plane?
Online.
So Scott's doing this. Right. Right. So those are hyperbolas. These are hyperbolas. So we're going to get hyperbolas that go down like so. And the same thing I'll do in dotted lines down here. And the surface is going to connect like so. So it's the way I think of this one is if you had a piece of like spandex fabric and you grabbed it right at that point, x equals 5 and y equals 5, and picked it up. And it's attached to the x and y axis. So let me see, I made some graphs that hopefully would help you visualize these a little better. So here's that graph. So here's the point up here at z equals, I did it from 0 to 10. So this would be z equals 100 up here. And it's the y-axis over here and the x-axis over here. And the surface is stretched up from there. So we get kind of a hyperbola shape there. And if we look here, it would be kind of curved down here. So that's what our surface looks like. And the origin is down here, so it's stretched up. And if we kept going, it would keep going up and up, but it would always be connected to the x and y axis. So that's one way we can visualize. That's one way we can visualize these functions. It's just picking some points and plotting them and kind of getting an idea of what it might look like. But if we have more complicated functions, we have to do something else. So let's think about what we did here, and we want to ask ask a couple of questions. If we had if we have a g of xy equals some function of xy minus 3, how would the graphs of f and g compare? So Caitlin says they'd be shifted. How would they be shifted? So we're remember we think of g or f as the z value. So our function value is like the z. So how they'd be shifted. So how would g be shifted from f? Down. So g would be shifted down 3 from f. So if f were the example that we had before, where our surface was kind of stretched up from the xy plane, if g was f of xy minus 3, it was x times y minus 3, that would just shift that graph down 3 units. What about g of xy equals minus f of xy? How would that graph be different? It'd be flipped where? So Charlie said something about the z. So the z would, where would it flip to? Negative z. So Hayden did this. Flipped. So it would be flipped, or it would be reflected in the xy plane. So, or flipped over the xy plane. So it just takes whatever our positive z values are and turns them into negative z values. How about g of xy equals 1/2 f of xy? What would that do? So Ann says shrink it. So if you're thinking, so what is, if you Emily says like a parabola, if you have a parabola and you do 1/2, if you had, makes it wider, but it's wider, but it's kind of squashed down, right? So this
Would it make like the Z length half?
right. So the z length would be half.
Yeah.
So it'd be squashed down, but it kind of widens it also. So this would be shrunk down by a factor of 1/2. All right, let's talk about, so this is just kind of helping us visualize some transformations of graphs. We just want to get kind of work a little bit on how we visualize these surfaces. So next we're going to talk about another tool that we have. And this, you're going to be a little bit familiar with these because everybody's seen this idea, just might not have thought about it in this context. So what we call these is contour maps or level curves or contour lines. This is another way we can visualize what these surfaces look like. To get an idea of what the surface looks like, we sketch curves f of xy equals a constant for different values of a constant to get an idea of what the surface is going to look like. Examples of this sketching f of xy as a constant is like a topographical map where each line represents a constant elevation, and based on how the lines are spaced, situated on your map, you can get an idea of what the terrain looks like. Weather maps, like isobaric maps, you get an idea of where lines of constant pressure are, so you can figure out where high pressure is, low pressure is. In physics, you sketch equipotential lines for an electric field. So that's a contour map or a level curve. That's the same idea. You know where the potential is constant. And the way that a contour map or the level curves or the contour lines help us is if the contour lines are far apart, it means that the function value is changing slowly. So that means your graph is going to be, your surface is going to be flatter where the contour lines are far apart. And if they're close together, it means that the function's changing rapidly. So like on a topographical map, when your elevation lines are very close together, that means you have some kind of cliff or a steep hill or something. So that helps us visualize what the surface looks like. And what we do for these, in order to draw your level curves, we set f of xy equal a constant and figure out what those curves look like.
Wait, when do we do that?
If we want to draw contour lines or we want to figure out what the level curves look like, we set f of xy equals a constant to see what the curves look like. If we have a 3-variable function or a higher variable function, we set f of xyz equal a constant, and we get level surfaces rather than level curves or contour lines. So we get level surfaces. So if we have a function of 3 variables, the function is going to be constant on a surface. This gives us level surfaces. So in your book, on page 893, we want to look at some examples of matching level curves to a function. Does anyone need to borrow
Will we borrow one?
a book? I have one book.
What page?
So we're on page 893, and we're looking at number 45 through 48. We want to match the function with its contour map. So number 45, I'll put it up here.
Oh, I guess that one.
So for f of xy equals e to the 1 minus x squared minus y squared. So which one is that one going to match with? C. So this matches with C. Now if you wanted to do this analytically, if they didn't give you the level curves and you needed to figure out what the level curves of this function look like, you would set e to the 1 minus x squared minus y squared equal a constant, and figure out what this graph is going to look like. So if we wanted to visualize this, what would we have to do here? Take the natural log of both sides, so we get 1 minus x squared minus y squared equals the natural log of a constant is just some other constant. I'm just going to call it C1. So this gives me x squared plus y squared equals some other constant. Because I take the 1 minus this constant is just another constant. So we get circles. So that's how we figure out that our level curves look like circles. And I made a graph of this one that just might be a little easier to. So here's that function. I know it's graphed in the book, but I just thought this might make it a little easier to see. And if we turn and look straight down onto it, our contour lines are those circles. All right, how about number 46? We have f of xy equals e to the 1 minus x squared plus y squared. We think D on that one? So our contour lines our level curves are hyperbolas. And again, if we want to analyze that, we say e to the 1 minus x squared plus y squared equals some constant. Take the natural log of both sides, so 1 minus x squared plus y squared equals some other constant, the natural log of a constant. And we rearrange this and we get y squared minus x squared equals some other constant. And this is the graphs of these for different constants are going to be hyperbolas. And our shape is that saddle shape. And let's take a look at that one. There we go. So if we look straight down on that one, I'll try to So here are hyperbolas this way. And if we think about where the function is level, where the surface is level along here, we're going to get a hyperbola along there and a hyperbola along there. For each level, if you think of this as like your elevation, if you're at a level elevation, you're going to get a hyperbola. So that's why the level curves of that function are hyperbolas. All right, what about number 47? We've eliminated some possibilities here. So f of xy is the natural log of the absolute value of x minus y squared. So Kaylin says b. So parabolas. And again, Caitlin's correct. If we want to analyze this, we say that the natural log of x minus y squared equals some constant. And this time we do the opposite. We raise each side to the raise e to the each side. So we get x minus y squared is some other constant, e to the c, and we get y squared equals x plus or minus some constant.
Isn't it the same constant?
Yes. So, and this gives us parabolas. And we should have here our constant, this should be a plus or minus because of the absolute value. Absolute value gives us a plus or minus. So this gives us parabolas. And let's take a look at that surface where we can move it around a little bit. So there's that surface. So what's happening here along this? What's happening here along this? It's a parabola. Why does the function look like that? Scott says because natural logs are mean. What's happening to our function there? Y minus x squared along here is a peak, a down peak. So it's right. It's like an asymptote sort of, right? Because our natural log is undefined. So this would be like a huge steep valley going down, 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 down. So let me try to rotate it, and we'll look at our. If we think about where the elevation is constant, I get parabolas here.
So what's the function going out? So we have the parabola and then it's
It's the same function, but as we get to where y minus x squared would give, because we can't take the natural log of 0 or a negative number, our function becomes undefined anywhere we get a 0 or a negative number in our function.
so
And that's
undefined.
right. So our function would be, so it's kind of like having an asymptote, but our asymptote is kind of like a curve. So our function would be undefined along that curve, right along here. All right, and then we have our last one. We only have one possibility left, so 48.
Can you show us, like, I don't really understand what the graph is of 48.
Yeah, I have a graph of that one also. It's a really cool graph. So here's our function, is this cosine function. And our graph, our level curves, it matches with graph A. And if we wanted to analyze it, we would say that the cosine of this, of x squared minus 2y squared over 4 is a constant. And we take the inverse cosine of both sides, so x squared minus 2y squared over 4 is some other constant, inverse cosine of whatever that constant is. And we get x squared minus 2y squared equals 4 times this constant. And these are ellipses. So our level curves are ellipses. And let's look at our function. So this is what our function looks like. So we get this wavy bit from the cosine function, from the trig function. So it goes down and back up and down and back up. And if we look straight down on it, those are our, now we see our ellipses. So everywhere that the elevation, if you want to think of it as elevation, oops, I didn't mean to touch it. Everywhere elevation is constant, we get an ellipse. That's
I thought that x squared plus 2y squared would be an ellipse. I think you wrote it.
oh, I wrote it in my example wrong here.
Yeah, you ended up with an ellipse.
Okay. So so to come up with this without just to try to plot this, pretty difficult. So that's what the contour maps or the level curves help us do. All right, and this should be a plus.
So, like on a test, would you give us a function and we'd have to draw the contour map to it?
Right. So I'd give you a function like this and say what are the level curves of this function.
Give us one this hard.
Well, this.
Oh,
So we're not graphing it. We're just figuring out what the level curves look like.
okay, just like what shape they're in.
Right. So you just do this and you say, oh, this is an ellipse. And then if you want to plot them, you just pick some values of C to plot. So you could say, C, if you said C2 equals 2, you could plot, and then you could plot some ellipses to make your level curves. But to analyze these, to figure them out, we set our function equal to a constant and see what that graph looks like in the XY plane. Let's see. On page, let's see, number 52. Let's look at number 52 in your book. It's asking you to plot level curves of x squared plus 2y squared for different values of constants. For c equals 0, 2, 4, 6, 8. So our level curves, it's asking you to plot our level curves. So what are our level curves going to be?
Ellipses.
Our level curves are going to be ellipses. We just set this function equal to each of these constants and plot those level curves. Looking at this function, if we say z equals x squared plus 2y squared, what does our surface look like? We know how to visualize this surface. We did this in
This circle that goes
so it's a circle, but is it a circle? It's an ellipse. So it's an elliptical shape,
It's ellipsoid.
elliptical paraboloid, right? If we look at z equals x squared plus 2y squared. In the xz plane, we get the parabola z equals x squared. In the yz plane, we get the parabola z equals 2y squared. So if I did just a really quick sketch of this, we'd have a paraboloid that's elliptical shaped, like so. So if we were to plot this, just thinking intuitively, I'm not going to plug in numbers, but if we did this on the xy plane, our level curves would look something like this. And then as we go out, they're going to get closer together because our function gets steeper. So it's really, really bad ellipses. But as we go further out, our level curves would get closer together because our graph is going to get steeper. So that's like looking down into this from straight above and mapping out where the curves are constant. Let's look at one more, and then let's see. One more like this. So this is number 56. We have f of xy equals a natural log of x minus y. This is a little trickier to visualize. See, and we want to plot for c equals 0, plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 2. So what are our level curves going to be? We set x minus y equal to our constant. So we get x minus y equals some other constant. So y equals x minus our constant. And we're letting our constants be 0, plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 2. So what are our level curves? So we're just in the xy plane. These are just lines with a slope of 1. So if we're graphing this, I'm sketching a quick graph. I'm not going to plug in numbers. So in the xy plane, we have lines with slope 1, and when we're closer to 0, our lines are closer together, and then they get a little further apart. And our lines, let me put a few more in here. I want to emphasize they're closer together here. So what is this surface going to look like based on what the level curves are telling you? Anybody have an idea? What do you, Danny? So Danny says this. Because it's really steep here and it's less steep out here. So let's take a look. So there's our surface. So Scott says, how do you know if it's in or if it's out? You'd have to plug in some numbers and see if they're positive or negative. But that's a good, from the level curve, you can't really tell. Like on a topographical map, you could look and see the contour lines really close together. You could be looking at a cliff going up, or you could be looking at a valley. So you have to have some other information to figure that out. So there's our surface. There's the line. Here's 0, and it curves up like so.
And curves up the Z.
Z is here, and the So it's at a tilt. Let's look back at our lines here. Here, let me go from above. Do it. Get it oriented how we graphed it. Come on. There we go. So here's our lines with slope 1, and it comes up above the XY plane. So we're looking at it straight down from the positive Z direction, and it curves up kind of at an angle. Let's go back. So these are the contour lines that we drew. So this would be down where it was really close to where it's on the XY plane, and then it's coming
Oh,
up
okay.
this way. Okay. All right. Let me just ask you a couple quick questions, and then we're done. If all the level curves of z equals f of x, y are circles, if all the level curves are circles, then the graph is a hemisphere. The graph of the surface is a hemisphere. True or false? False. Charlie says false. Why? The cosine one, it can go up and down. Or the very first example, that exponential function we looked at, the level curves of that were circles. All right. I'm going to stop. Homework.
Oh, Scotty, you're an academic. We're meeting in the student center today during the Christmas.
So what? Everyone is?
No, just for academics.
Oh, I'm an academic.
Okay.
Nobody told me I was.
But yeah, we
I know. I'm gonna send you a text. I've been busy.
You
Matt
have a list
should
of
have
who's
sent
who?
you, and yeah, I have a list.
definitely did not get an email.
I should only contact you guys at some point in time. Okay.
Okay,
A lot of these are about visualizing or describing, not necessarily solving things.